All right, today we're talking about Merg-E, a domain-specific language for the Web 3.0 world that's built on a pretty radical idea. What if you just threw away general-purpose features in exchange for extreme provable security? We're going to look at how it fits into a stack that's using both classical and quantum-resistant crypto, which makes it a really fascinating case study in high-stakes, minimalist language design.
So here's the plan. We'll start with what Merg is and its place in the Web 3.0 stack. Then, we'll get into its core design philosophy, which leads to some, well, truly unique language features. From there, we'll pop the hood and look at the runtime architecture. And finally, we'll see how it all plugs securely into its environment.
Okay, let's get right into it. First up, what exactly is Merg-E, and maybe more importantly, what specific problem was it built to solve?
At its heart, Merg-E is a really specialized tool. It's for building secure Layer 2 components, things like nodes, bots, and backends that need to talk to cryptographic systems. Think of it as the secure glue for stuff sitting on top of blockchains like CoinsDance. It is absolutely not trying to be the next Python or TypeScript. Its scope is deliberately, and I mean aggressively, narrow.
You see, Merg-E was really born out of a specific architectural pain point. When you have a system that's built on least authority principles at the crypto layer and at the file system layer, dropping a general-purpose language in the middle creates this messy and potentially insecure gap. All those language bindings and extra features, they just introduce a bigger attack surface. Merg-E is meant to be that clean, secure, and tightly integrated bridge.
And you know, the name itself actually tells you a lot. It's a practical merge of a few different paradigms, borrowing heavily from data flow and functional programming. And that E, that's a direct hat tip to the E language, which is where it gets its object capability security model. And that's a powerful idea. You don't just get access to an entire object, you get access to specific capabilities, or things it can do.
This leads us right into Merge's design philosophy, which, I have to say, is fiercely opinionated. This is where you really see how those security-first ideas are baked right into the language itself. These rules are all about two things: minimalism and security. For example, variables are immutable by default. You actually have to go out of your way and write mutable to change that, which makes the safe path the easy path. The language also has just two core data structures. That's it. You get DAGs, directional acyclic graphs for structured data, and data frames for tabular data. And, crucially, it has this model where the runtime, not you, the programmer, gets the final say on parallelism.
And this quote here really gets to the heart of it. The language isn't trying to be academically pure. It's a pragmatic blend of ideas from the actor model, data flow, functional programming, and object capabilities, all of it tailored for one job: building secure Web 3.0 data flow pipelines. Now, this concept of DAGs all the way down is absolutely central to the design. It creates this incredibly unified model where everything, from the language features you can use, to the permissions a process has, to your own application's data, it all follows the exact same fundamental pattern. This kind of radical minimalism is what keeps the language core so simple.
Okay, so that's the philosophy. But what does this actually look like when you're writing code? Let's dive into a couple of key features that really show off this design philosophy in action.
This slide is a perfect illustration of that focus on least authority. In a lot of languages, when you create a closure, it just kinda sucks in the entire surrounding scope, which can lead to you accidentally leaking permissions. Merg-E makes you stop and think. You have to use this special double close syntax to explicitly declare exactly what authority and mutable state a closure is allowed to have. It makes the flow of power auditable right there in the code. The language also completely reimagines imports. Instead of a blanket import statement that just pulls in a whole file, Merg-E uses a merge keyword. This thing is surgical. It performs a precise, contract-based import, making sure the function you're bringing in has the exact signature and behavior you expect. It's another layer of explicitness and security. And get this, to really hammer home this philosophy of minimalism and to future-proof the language, Merg-E has exactly one reserved keyword. Just one. Its scope. Everything else, from if statements to type definitions, is defined within a DAG that's anchored to this single, universal root.
All right, let's pop the hood and get into the engine room. How does Merg-E actually execute code, especially with that whole zero-assumption parallelism idea? Well, it all starts with something called Yggdrasil. Now, this isn't your standard first-in, first-out queue. It's a pretty sophisticated, DAG-based database of all the work that needs to be done. Every task is just a node in this big graph.
complete with its own scope, its dependencies, and its code.
And then there's Nidogger. That's a scheduler. It intelligently walks this task database. The idea is that it chews on the roots of the Yggdrasil DAG, and it manages execution by respecting dependencies, prioritizing work, and then handing off those tasks to worker threads. You got to admit, the mythological names really do make these core concepts stick.
Now, this architecture is what makes that zero-assumption parallelism idea actually work. The language itself just expresses intent, right? It says a task can be parallelized, but it's up to the runtime to decide how. So a hint from a developer might get totally ignored by the simple, single-threaded develop runtime, but the enhanced runtime could see that and go compile it to run on a GPU. There's a really clean separation of concerns here.
Okay, finally, let's look at how this all plugs into the ecosystem securely. I mean, a language is only as useful as its ability to talk to the outside world, especially when it comes to sensitive data like API keys.
Merg integrates with a tool called Innuendo Vault FS. You can think of it like a specialized file system that walls off secrets. It doesn't just look at the user ID. It identifies a program by its unique executable path, creating a kind of private vault for each individual application.
And this is where that whole principle of least authority becomes totally concrete. The application code never, ever asks for a raw secret key. It asks for a capability, like a signer function. The Merg-E runtime then goes and gets the raw key from Vault FS. It creates a new signing function with that key safely embedded inside, and it hands the function back. So the application gets the ability to sign things, but it can never actually read or steal a key itself.
This whole process is enforced by a really simple but incredibly powerful convention inside Vault FS. If you store a key in the code namespace, the application can read it. But if you put it in the runtime namespace, only the runtime itself can access it. It's a clear, hard boundary that lets the system manage access to your most sensitive secrets.
So to wrap it all up, Merg-E is a really fascinating experiment in language design. It knowingly sacrifices the convenience you get with a general-purpose language for extreme specialization. By focusing on security, minimalism, and a runtime-agnostic approach to parallelism, it offers a toolset that's specifically hardened for building trustworthy, high-stakes systems in the Web 3.0 world.
And that leaves us with a pretty provocative question, doesn't it? As our systems get more and more complex, and the cost of a security failure gets higher and higher, is the future in building even bigger general-purpose languages? Or do we need to start embracing a new generation of minimalist, specialized, secure-by-design tools just like Merg-E?